Something else we can look at when we're talking about our galaxy is what's our mass? Well, previously, when we've talked about mass, particularly with binary stars, we mentioned that you can figure out the mass by looking at how the stars are moving. Specifically, we can use Kepler's laws to help us determine the amount of mass. We can look at how the sun is moving throughout the galaxy, and that's going to help us start to understand the mass. Now, one thing to understand, looking at the sun, how the sun is orbiting around the center of the galaxy will only tell us the mass inside of the sun's orbit. It's not going to tell us the mass of the entire galaxy, just what's inside. So as we've looked at very distant objects, we've found that our sun is actually traveling at around 230 kilometers per second. Notice that's second, not hour, which translates to over 500,000 miles per hour. That is really, really fast. And yet, here on Earth, we're going that fast because we're traveling with the sun. We don't notice it. And the key here is because we feel acceleration. Accelerations lead to forces. Velocity doesn't. So, because we're going at this speed and it's pretty well constant, we don't notice anything. Now, what this means about the motion of the sun is that it actually takes about 230 million years for the sun to orbit once around the center of the galaxy. Based off of this, we have determined that inside the sun's orbit, just inside the sun's orbit, there's somewhere around 90 billion solar masses of material. Around 90 billion. Now notice that the sun is not at the very edge of the galaxy. What this means is that 90 billion is not the mass of the entire galaxy. If we want to figure out the mass of the entire thing, we're going to have to look at the motion of stars way out here at the very, very edge. So as they orbit around, they'll actually include everything within the galaxy. Well, as we have done this, looking at those stars at the very edge, we've been able to determine that our galaxy contains around 1 trillion solar masses of material. Okay, so that's going to be spread between stars and interstellar medium and other stuff. Okay, based off of current observations, we think that within the galaxy there's between 200 and 300 billion stars. Okay, all of the rest of that stuff is going to be interstellar medium and other things. Here is our third lecture quiz question. According to Kepler's laws, what happens to orbital velocity as distance increases? A. Orbital velocity increases. B. Orbital velocity remains the same. C. Orbital velocity decreases. Or D. Kepler's laws do not apply to orbital motion. Go ahead and think about it, and we'll discuss in just a bit. Alright, so what does Kepler's law say about orbital velocity as distance increases? Well, the farther out it is, the slower it should go, which is C. Orbital velocity decreases with an increase of distance. As we've looked at the motion of stars in our galaxies, we've actually found something a little bit surprising. They don't actually follow what we would expect based off of Kepler's laws of motion. So most of the visible mass in our galaxy is located close to the center of the galaxy. We have a lot of stuff in the central bulge, and then a lot of material in the disk. The disk is more packed towards the center and less so at the edge. Now, what this would predict is that as we are moving farther and farther out in the disk, we would expect stuff to slow down. So in this image, what we're looking at is known as a velocity curve. Up and down, we have the velocity, or how fast the material is moving in the galaxy, and then along the bottom we're looking at the distance. So right through here, this is the central bulge. We have lots and lots of stuff, all pulling, so things speed up a lot. As we move out towards the disk, we would expect stuff to start slowing down according to Kepler's third law. Remember, the farther away something is, the slower it should go. What we have found is that that's not the case. A is what is predicted. The farther out you go, the slower it goes. B is what has been measured, where the disk pretty much stays at the same speed all the way out to the edge. This is actually our first clue of the existence of dark matter. Now we're going to spend more time talking about dark matter later, but the motion of stars in our galaxies is actually one evidence that dark matter exists. Now, if we want to look at the very center of our galaxy, we cannot use visible light. The interstellar medium blocks and scatters visible light, so we can't see what's going on if we use visible light. However, infrared light is able to pass through the interstellar medium, as well as X-rays and radio waves. So if we want to study the very center, we need to use infrared, radio, and X-ray. Well, as we have looked at the center of the galaxy using infrared, we're actually able to watch stars orbit. Each of these dots corresponds to the position of stars in a given year. So we've actually been able to watch how it is that these stars are moving. Now, these white ovals are showing the orbits of these stars as calculated by their general motion. Notice that all of these stars are orbiting something right here at the center of this image. We don't actually see anything there, but based off of how these stars are moving, whatever is there has to have around 4.1 million solar masses. So what's something that has tons and tons of mass that's not giving off any light? Supermassive black hole. This is the location of the supermassive black hole at the center of our galaxy. It is known as Sagittarius A star. Sagittarius because it's in the constellation Sagittarius, which is towards the center of our galaxy. Now, as we look at the center of the galaxy using X-rays, we see these lobes of hot X-ray emitting gas above and below the general plane of our galaxy. We believe that these radio lobes are actually remnants from a previous time where the supermassive black hole at the center of our galaxy was active. What we mean by active is that there was lots and lots of stuff around it, so it was able to pull in all of that material. And as that happens, it can actually eject some of that as this hot X-ray emitting gas.